All right, so, I told you that one of the keys to integration by parts was to recognize that you can transfer the derivative, and that if you have like x to powers, that power will come down every time you do one of the iterations. But sometimes you don't choose that. And in one of the homework problems, that's exactly what happens. You have a natural log along with an x to the fourth power. So if your instinct initially is to make u x to the fourth, that's usually a natural instinct. But in this problem, you have to realize that the letting u be natural log of x is the better approach. Because when you take the derivative of natural log of x, you get 1 over x dx. And then if you let the dv be the x to the fourth, then when you integrate that, you get x to the fifth. Of course, there's a 1/5 in front. And when you look at the diagonal, you put these two together, that's going to be a nice polynomial, right? When you multiply these two together, the x to the fifth, that's really like, just x on the bottom, so one of the x's cancels, and you get right here. Here it is right here. Here's our voodoo right here, v du. One of the x's cancel, you just get an x to the fourth here, you pop your 1/5 out, and then you just use power rule on that. Once you use your power rule, you'll get another 1/5 to pop out, and there's the result. So that's one of those things, again, where I can show you a bunch of problems. I can spend almost 2 hours showing you problems. You get to the homework, you're going to see some slight variations, and it's important that you work through those. All right, next one. The next one was more straightforward. So the appropriate choice of u here would be t, and then you let your dv be the sine 5t dt. And I guess the key to this problem is on that integration step when you go up to v, is that you recognize you've got to get that negative 1/5 out there to account for the chain rule. And then from there, you just set up your table, and your voodoo, this part, the diagonal, is going to just be a cosine function with no more t's in front, and you should be in business from there. So that's just rewriting ultraviolet, or u times v. And then this right here turns into a cosine after you pull the 1/5 out. Antiderivative cosine of 5t is, again, another 1/5 comes out, sine 5t. That hits that 1/5, you get 1/25. Questions, comments, concerns? Each problem's worth 60 points. So if you, mess something up, if you forgot the 1/5 or something, I'll take off some points, but you can still make 100. Yes?
Does that always have to be in the case of sines and cosines and trig functions, does it always have to be those on that side?
Well, if the other option is a polynomial, like t is like a polynomial, t to the first power t squared, then, yes. I don't want to say always, because that, I would be kind of opening myself up to someone coming up with an integral where it wouldn't happen that way, because I'm sure we could produce one where you would rather have the sign here, right? This is where kind of seeing ahead, though, and understanding how the integration by parts works, seeing kind of 4 steps ahead of what this diagonal integral is going to be. If you can visualize that before you actually set it up, that helps you make the choice. If not, you have to just try, and of course that's going to take time, right? So I'm timing you on these because, I was talking to my other class this morning about this. Your test is a week from today. And your test will cover everything that we cover up to the end of today. All right? Tuesday, we have scheduled a review day, which is like unheard of. I will do some review, but don't come in expecting for me to just be like, well, here's a copy of what you're going to get on the test. Like, here's a copy of the test, and I'm just going to change number. Don't expect that. The review day is going to be me coming in here and me taking questions. Hey, I'd like to see another one like this. And if it's something way out of the, spectrum of what I would ask on a test, I would say, you know what, come to my office, I'll show you that. I wouldn't focus on that right now. But it's more going to be me taking questions, And if I come in on Tuesday and nobody has questions, then we'll just move into the material that's coming up. It wouldn't be on the test on Thursday, but we would just keep proceeding. Got it? So it's your opportunity. It's like an open Q&A type thing. All right? What else was I going to say? We'll talk more about the test. All right? I don't know if we'll have time today at the end of class, but we'll talk about it for sure on Tuesday. You're going to have a quiz on Tuesday, but I'm going to tell you exactly what's on it. You ready? Sure. Okay. I want to see all your homework on Tuesday. So you need to come to class, and you need to have your homework in one place where I can walk around the classroom. And it doesn't have to be like, hey, you skipped number 13, you know, I'm going to take off. I just want to see an honest attempt at the homework. Why? Because there's no way I can force you to do homework, right? But if I give you as a quiz grade, maybe that'll encourage you. So I'm terrible with analogies. Have I not already made that clear? Okay. So this right here is an analogy that I was thinking of. So like, it looks like somebody slit their wrist. That's not what I intended it to look like. What I intended it to look like was just somebody bleeding. So, you know, what is like the number one step if you get a cut, like, you know, a pretty good cut where you're bleeding pretty good? What's the number one step? What is it?
Apply pressure.
Apply pressure, right? Apply pressure. Is that right? Good enough? Okay. You apply pressure, right? This class requires you to apply pressure at all times. If at any point in time you stop applying pressure to this class, you will bleed out. That's a pretty good analogy, I think. Okay, so you walk into the class kind of bleeding already, and you have to apply the pressure and always apply the pressure. It's the way it goes. Okay. I think that was a good one. I think we're ready to move on. Will you switch? Thank you. Apply pressure. Constant applied pressure. What's that?
That was the best one.
That's the best one. I'm gonna stick with that. Yeah,
I was wondering, where is he going?
my teacher was showing us like how to slit your wrist. If you're in Cal 2, like you go home and slit your wrist. No, that's not what I'm saying. Okay. All right, so we need to finish up some stuff here, wrap up some loose ends on integration by parts. And then when I'm done with that, I'm going to move into the next section. And like I said, what I covered today will be on the test, but the stuff from the next section we are not in any way going to get through at all. We're just going to hit just the very beginning of it. And I think when you see the problems, you might, my other class at least, I got the feeling that they kind of were like, oh, okay, that's a little better than integration by parts. So they were like kind of happy to see it. And I'll put, you know, one of those or two of those on the test. So let's first kill off this section. And what we had here was we had done everything up to pulling a rabbit out of the hat. That was the last problem we did we did e to the alpha x cosine beta x, and it was kind of really weird how all the alpha and betas came into play. And what we haven't seen is how you can get an integral where you're going to use integration by parts, but you don't see it right away. You actually have to make a traditional U substitution first. And the U substitution doesn't even look natural. So here's an example. I'm going to start with not the one that I just had up there. I'm going to make up another one. There's one like this in the book. It's like theta cubed cosine theta squared d theta. So we're using theta instead of x. Big deal, right? So if we were to be thinking about integration by parts, right? And by the way, today I'm not really going to call on anyone because a lot of this is me like, let me show you first. We might be thinking initially, okay, we've got a nice little polynomial in theta. So I know if I use integration by parts, that's going to start coming down in powers, right? Every time I do an iteration of it, the power will come down. That seem fair? The problem with that is if I choose this to be my u, this is my dv, right? This part right here. And can you integrate cosine theta squared? No, you can integrate cosine theta, but cosine theta squared doesn't just go up to become sine theta squared. It's the squared on the theta that causes that problem. Understand? So, doesn't look like that should be my u. Maybe then that should be my u. I don't know. Well, what about making a substitution first, before we even try integration by parts? And for substitution, I told you try and look for something in its derivative, right? Do you see something in its derivative? You see theta cubed. What's its derivative? 3 theta squared. But that theta squared's trapped in a cosine, and it's not allowed to be trapped. So my only other u substitution that I could do would be what? Just theta squared. Now that doesn't seem like it's going to get us anywhere, because if I choose theta squared to be u, then the derivative of that is 2 theta, and I don't have 2 theta, I have 2 theta cubed. So I'm off by more than just a constant, right? I'm off by a couple of powers. By what? Yeah, exactly. That's what you need to see. You need to see that that theta cubed could actually be split apart as theta squared times theta. And then it would kind of appear there. So let's try it. Let's just go for it and see what happens. I'm going to make just a basic substitution. U is theta squared. I know that the derivative of that is 2 theta d theta, right? So I know I'm going to be able to replace this. I'm going to be able to say cosine u, right? D theta, I've got to be able to replace here. Got d theta, but I also have a theta. So that's where you see that, oh, well, why don't I peel one of those thetas and just push it to the back over here? So if I rewrite the integral, make that theta squared cosine theta squared, then I have a theta d theta. It's just me rearranging multiplication there. And now you see it? You see that we've got theta d theta right there is this. So I'm just going to multiply both sides by a half to get rid of that 2. So half of du will replace theta d theta. So if I'm kind of knocking things out as I go here, this is checked off, right? I've got that. This is going to go away. This right here is going to go away. I just need to handle that theta squared that I still have out there. But I got lucky. Theta squared is u, right? What if this was, what if this happened to have been theta to the 4th? Like this started out as theta to the 5th. I peel one off, I have theta to the 4th. Then it would have been u squared, right? Because if theta squared is u, then that would have turned it, I could square both sides and say u squared is theta to the 4th, right? So there's ways algebraically that I could have handled that. That's not what happened, but it could have happened. Okay, so now let's just plug in. This new integral becomes theta squared is u, cosine u, right? U, cosine u, and then theta d theta is half of du. Why don't we pop the half out and du? Now we can do your integration by parts, because, and this is where we have to be careful with letters, because in all of our integration by parts, we had u and v, didn't we? U and v. But I've already used up u, haven't I? So if I'm going to do integration by parts, I want to kind of start separating myself from the idea of that uv and start thinking more about the formula. The formula says I pick one of these, its derivative goes to the new integral, the other one, the integral goes, right? So this one, the derivative of that will go into the new integral would be just 1 or something like that. 1 du, doesn't matter. And then the integral of this would go into the new integral, and I can integrate cosine u. Couldn't integrate cosine theta squared, but I can integrate cosine u. All right? Pardon me?
So is u in this?
Yeah, so how are we going to handle this? Well, the way that I recommend you do it is just use a different variable. All right, so I'm going to make a table now. It's like the whole problem now has reduced to this one, right? And I'm going to make a table for my integration by parts. And normally I would put u here and dv here, right? I haven't used v, so I'm going to go ahead and put the dv, but I'm not going to put u up there. I'm going to choose a different letter. I like to use W. Doesn't matter what you use. Just don't use U. All right, so I'm going to call W U. All right, this one. And then I come down with this. dW is du. And then I have dV, which is this part right here, cosine u du. And then I integrate that up to V to get sine u. That all makes sense? And again, I'm not going to be able to use the mnemonic of ultraviolet minus voodoo here because I've got W's and V's. And so instead it's a matter, I like to look at the table. How did it work with the table? This was equal to this times this, right? Minus integral of the diagonal. So what's this piece here? U sine u minus integral and then the diagonal. Sine u du. Everyone with me? Question, yes?
What about the constant?
Constant. Oh, when I integrate up here? Is that what you're talking about?
No, from the one half.
Oh, thank you. I forgot the 1/2 completely.
If you were to have another constant inside of voodoo, would you just move that out and multiply it with that constant?
If I had a constant where? What?
And voodoo,
In this piece right here?
Yes.
Yes, that would come out right here.
and you would multiply it.
And then this would come and hit it. So look, everyone see I missed the 1/2? Okay, so I need to put that in there. Thank you. 1/2 needs to go here, and then I'm going to put a bracket like that. Okay, so that 1/2 will actually have to distribute through to this and this integral. Because this is actually two terms, right? Isn't it? Two different things. And if the 1/2 is sitting in front of it, 1/2 has to go to both. All right, we can integrate sine u, can't we? Antiderivative of sine of u? Negative cosine u. But I already have a negative, right? So it's going to wind up being a positive cosine. So this becomes equal to 1/2 bracket u sine u, and then plus cosine u, and then plus a constant, right? Now, it doesn't matter where you put the constant. I'm going to put it out here. One of my students in my other class said, wait a minute, if you have a plus constant here, doesn't the 1/2 have to multiply to it? Well, 1/2 times a constant is still a constant, right? So it doesn't matter that it's half of something, because that can be any number we want, right? So this still accounts for all possible numbers.
And substitute u back.
Now, last step, replace u with what u was. U is theta squared, wasn't it?
Yes.
And we're there. And I'm actually going to distribute the 1/2 through also at the same time. So the 1/2 is going to go to this term and then to this term. So I will have 1/2 u is theta squared sine theta squared plus 1/2 got distributed through cosine of theta squared plus c. And that's it. If we take the derivative of this, we should get theta cubed cosine theta squared. Should we do it? No? You don't, who wants to see if it's right? I don't care. You're happy? You're satisfied? Okay, you can check it on your own. All right, box it up, we're done. Okay, you see how that worked? Substitution followed by integration by parts. Here's another one. This is the one that's on the notes. The antiderivative of this is not just e to the root x, right? Life would be too easy if that was it, right? This is not e to the root x plus c. Why is it not that? You take the derivative of the e to the root x, you get itself, but then chain rule is derivative of what's up there, and that's not there, is it? So that's not it. I don't see a basic U substitution. Like on the last one, remember we did the theta squared and we could kind of see we're going to be able to mess with that theta cubed to get it to work. Here, if you choose U to be root x, I don't see its derivative anywhere, do you? Right? The derivative of root x is 1 over 2 root x, so I don't see it. Do you?
Square both sides.
Square both sides of... Okay, so yeah, let me try that. You're saying let u be equal to root x? And if I square both sides what?